In Chapter 18, we will be looking at different aromatic compounds. Many pharmaceuticals contain aromatic compounds. You can see the list of the different structures up here, and these are not the common names, so you might not recognize some of them, but you can see that they have the benzene ring in common. So some antihistamines, such as phenoxyphenidine, bind at the H1 receptors, which make you sleepy, and they have a sedation effect on these antihistamines. So you can see that fexofenadine has the two aromatic rings here, and this tertiary nitrogen. And all of these drugs up here had that same common core of the two aromatic rings and that tertiary nitrogen here. And these are mostly nonpolar molecules. The second generation of antihistamines, which are non-sedating, are polar. They have these carboxylic acid residues on the end and are HCl salts. These ones can bind to the same H1 receptors, which generally would make you sleepy, but these ones do not. These are also polar, and they do not cross the nonpolar environment of the blood-brain barrier. So aromatic compounds, or arenes, include benzene and benzene derivatives. Many of these aromatic compounds were originally isolated from fragrant oils, and things that had a smell used to be what was the definition of aromatic compounds. But now we know that many of these aromatic compounds are odorless. This class of compounds is used to describe compounds that have similar chemical behaviors, and these are very common. So we're familiar with benzene, which is the six-membered ring with 3 double bonds. Toluene is a form of benzene, but has a CH3 group. This is the common name. Orthoxylene has 2 methyl groups that are at the 1 and 2 position. So these are the common names. We can see a list of the pharmaceutical drugs here that have aromatic rings. We have Lipitor, which lowers your cholesterol. There's 3 different aromatic rings here. There's drugs for treating angina. This is the aromatic ring, but this one here with the double bonds is not aromatic. There's Prilosec or omeprazole is used to treat acid reflux, has the aromatic ring here. We want to move away from just thinking that the benzene ring is the only aromatic ring, and we'll see that later on. So you can see these different lists of drugs that have the aromatic compounds in them. Benzene is generally the parent name for derivatives that have one substituent. So for this one here with the chlorine, this is chlorobenzene. With a nitro group is nitrobenzene. And if you have an ethyl group, this is ethylbenzene. And then there are these down here that have, these compounds that are here that have common names. We already saw the toluene. This one is phenol, which you saw in chapter 13. This one is anisole with a methoxy group. Aniline has an NH2 group. This is benzoic acid. Benzaldehyde. Benzaldehyde. This one is acetophenone. And this one we saw in lab, this is styrene. So you will need to know these common names. If the substituent is larger than the ring, the substituent becomes the parent chain. Just like in this example, the ring is smaller than the longest carbon chain. This was treated as a cyclopropyl group. Here we have a chain of 7 carbons. This group here, if benzene is coming off of something, is a phenyl. So this would be 1-phenylheptane. This one here is tetraphenyl cyclopentane dione. There are 4 phenyl groups coming off of here. So this might sometimes be written as the cyclopentene dione, cyclopentadienone, and we can use pH, which we've seen already, to represent phenyl groups. And sometimes the phenyl group is represented with the phi signal, the phi Greek letter. These are all representations of the phenyl group. The common name for a dimethylbenzene derivative is xylene. So this is dimethylbenzene. This is orthoxylene. And ortho has the 1-2 relationship. This is metaxylene, which is 1-3. So you could call this orthoxylene or 1,2 dimethylbenzene, or this is 1,3 dimethylbenzene. If they're across from each other, this is paraxylene or 1,4 dimethylbenzene. If you have more than one derivative or substituent on a benzene ring, you want to identify the name and parent, assign a locant to each substituent, and then arrange them alphabetically. In the first example here, we don't have any parents that are common with the nitro group, but there is one with this methoxy. This is anisole. So then this would be number 1, where that main group was, and this nitro group will be at 2. So this is 2-nitroanisole. Or it can be ortho-nitroanisole. Both of those are correct. This is the parent here with toluene. So we have metabromotoluene. This is considered 1, so this would be 3-bromotoluene. With the aldehyde is our parent here. This would be 4-chlorobenzaldehyde. Or para-chlorobenzaldehyde. And this one here, the parent there is benzaldehyde. This is meta-isopropyl benzaldehyde. If you have 3 substituents, the parent here is phenol, where this is 1, this will be 2, 4. So I have 2,4-dinitrophenol. We've already seen that aromatic structures have resonance contributors rather than just being in equilibrium. So we've seen benzene with the double bonds drawn in different positions. If you move all these one position in the resonance, we get this structure here, and that's why we've seen benzene written with the circle around it. Benzene is also a stable compound. If we look at Br2 reacting with an alkene, which we saw in chapter 9, you get the transaddition of bromine relatively easily. But if you do Br2 with benzene, that same reaction, there's no reaction. However, if you do this reaction with this 8-membered ring with alternating double bonds, we get a reaction here. So this benzene is very stable and doesn't undergo the same reaction. If we try to reduce cyclohexene with hydrogen, it will take 120 kilojoules per mole. To do cyclohexadiene, it's 232. The expected for benzene would be 360 kilojoules per mole, but the actual observed is around 208 kilojoules per mole. So we saw in the last slide that cyclooctatetraene does react, and we saw that it was fully conjugated, but it reacted with bromine, whereas benzene didn't. So some fully conjugated cyclic compounds are reactive rather than being stable, like benzene. Compounds that are fully conjugated and cyclic can be reactive and not stable like benzene. In order to have an aromatic compound, we must fulfill 2 criteria. The first is that it must have a fully conjugated ring with overlapping p orbitals. Such as in benzene, all of those are sp2 carbons, pi orbitals, while all line up and they overlap. The second criteria is that it must meet Huckel's rule. Which is that an odd number of electron pairs, or 4n plus 2, there must be an odd number of electron pairs. Or the total number of electrons equals 4n plus 2. So in the case of benzene, we know that benzene is aromatic. It has 3 pairs of pi electrons. So benzene has 3 pairs of electrons, which is odd. So that makes it aromatic. If we want to use the 4n plus 2, the total number of electrons is 6. So the way that you would do this is 4n plus 2, and then solve for n equals 1. So where n equals a whole number. So if you end up with n being 1/2, it is not going to be aromatic. You can have an anti-aromatic compound. This is where you have a fully conjugated ring with overlapping p orbitals, just like in the first one. And then you have an even number of electron pairs. Or the total number of pi electrons equals 4n. So in the case of cyclooctatetraene, this has 4 pairs of electrons, which makes it the anti-aromatic. And if we do the equation here, there's 8 equals 4n, n equals 2. So 4n plus 2. So n equals 0, 1, 2, 3, 4. So if you come up with a half or 1.5, 2.5, then it's not going to be anti-aromatic. So in both situations, the aromatic versus the anti-aromatic, we have a fully conjugated ring with overlapping p orbitals, but the number of electrons will be different there. So these are called Frost circles, and it's a way of representing bonding orbitals. And we can see here that the number of bonding orbitals is always going to be an odd number. And aromatic compounds will always have that odd number of electron pairs in each of these. So in a 4-membered ring, you're going to have 2 electrons. In a 5-membered ring, you need 3 pairs of electrons, etc. You can go down the ring here. So in a 6-membered ring for benzene, you need to have 3 in order for it to be aromatic. In a 7-membered ring, you need to have 3 pairs of electrons in order for it to be aromatic. And you can see that and so on and so forth. This is not something that you'll have to duplicate or memorize. Aromatic compounds don't have to be just benzene. Annulenes are rings that are fully conjugated, and they are bigger than just the benzene. So you can see the alternating single bond, double bonds here in the 10 annulenes. So there's 10 carbons here. This one has 14 carbons. This one has 5 pairs of electrons. So that would be aromatic, and this one has 7 pair. So this one would also be aromatic, according to our rules that we established on the last slide. Sometimes rings must carry a formal charge in order to be aromatic. If we look at cyclopentadiene, we have a base that can grab a proton. The pKa of this proton happens to be around 16, so the OH minus can grab that, which makes this a negative charge here. That should be water. This would you know the pKa is around 15.7. If you had these electrons now, we went from having 2. This was not aromatic before because this was not a p orbital. But when you take this electron and put the electron pair here, now we have overlapping p orbitals and we have an odd number of pi electrons. We have an odd number pair of electrons. We went from having 2 to 3, so this is now aromatic. So this was not conjugated. This one is conjugated. And then odd electron pairs. And you can see the resonance structures for each of these. So the cyclopentadiene, if it wants to be aromatic, must carry a negative charge in order to do that. And the anion is stabilized by resonance because of the aromaticity. So there's that continuous system of overlapping p orbitals. The ring systems, some have to carry the formal charge. That doesn't mean that it's going to be negative. This is a tryptolium ion. It's a 7-membered ring, and when it carries a positive charge, it now has an odd number of pi electrons, and it has overlapping p orbitals. Cycloheptatriene. This is not aromatic. It's not conjugated. It does have the odd numbered pair of electrons, but that not conjugated makes it not eligible to be aromatic. If we pull a proton off to have the positive charge there, we have an odd number of pi electrons and the conjugation. So this one, like the last, is resonance stabilized and is aromatic. Heteroatoms, or atoms other than C or H, can also be part of the aromatic ring. We can see pyridine here. This is just an N, and then we can see the p orbitals that are overlapping here. This is a sp2 hybridized orbital. The lone pair is sitting perpendicular to the rest of the pi orbital. So this one is aromatic. In pyrrole, there's a lone pair here. Sometimes the lone pair is necessary on an atom in order for it to be aromatic. So if we look at pyrrole here, if we don't include the lone pair from nitrogen, we only have 2 pairs of electrons, which is the even number. If we include the electron pair from nitrogen, now we have a continuous pi electron. So this is part of the p system. This is also aromatic. If a lone pair is necessary to make it aromatic, the electrons will not be as basic. So in this example, we didn't need that nitrogen lone pair. So if it picked up a proton, this pKa is around 5.2. This compound is still aromatic. With pyrrole, if we grab a hydrogen, this electron pair is needed in order for that compound to be aromatic. So if this picks up a proton, the pKa is around 0.4. So this one is not as basic. And this one is not aromatic. So you can look at these compounds and determine if they're aromatic or not aromatic. This first structure, I have 2, 4, 6, or 1, 2, 3 pairs of electrons. This is aromatic. This one here does not have the conjugation system, so this is not aromatic. I have 1, 2, 3, 4, and the lone pairs from here contribute to that, so that's 5. This is aromatic. This is not cyclic, so this is not aromatic. It is conjugated, but not aromatic. Here we have 1 pair of electrons, which is odd. It's cyclic. There's p orbitals in all of this, so this is aromatic. This one is not conjugated because we have sp3 there. This one is not. This one is like the nitrogen. The S has electron pairs here that can donate to the p orbital, so this one's aromatic. And we saw that this one earlier, we have 4 pairs of electrons. This is anti-aromatic.